Okay, test review. All right, so we're talking about, in Unit 10 here, the trends on the periodic table, being able to look at a periodic table and know some facts about the element, maybe compared to another element. I do have some review questions here. Remember, these are going to be multiple choice. We're going to use our responders to answer all of the questions on the test tomorrow. All right, so why did Mendeleev leave blank spaces? The reason he did that was when he was doing his pattern on the periodic table, or the repeating properties of elements, he realized that the elements that they then knew just didn't fit the pattern. And so he left spaces because he believed there were undiscovered elements that would fit the pattern on the periodic table that he had according to, remember, increasing atomic mass. He did mass. They didn't yet know about protons, so they couldn't do atomic number. Okay, so other reason, someone's knocking at the door. I'm ignoring them. I don't know if you can hear it. That's always fun. All right, so the other reason, or the other thing that he did was he predicted the properties of them. He predicted those properties then when he left the blank spaces, and he was proved correct on that. He was not proved correct on the exceptions to the pattern according to increasing mass, but he was according to leaving those blank spaces. All right, so how does atomic radius change down a column? First of all, atomic radius is the size of the atom. It's from the nucleus to the outermost electrons. And as you go down and as you go across, well, it increases going down and it decreases going across. Ionization energy, which is the amount of energy to remove electrons. Remember, we talked about a first ionization energy, a second ionization energy, a third ionization energy, etc. in that one activity we did. Increase, decrease. It's the opposite of radius. And once again, same pattern for electron affinity. Electron affinity, how much the energy is going to be put forth to gain an electron. So if I asked a question such as this, are metals high or low? Well, in general, in the radius, since remember the metals, we have the stair step, the non-metals located above the stairs, the metals below the stairs, and then we have these metalloids, touching the stairs. Non-metals in general, according to these trends, well, if you're increasing going this way, the non-metals tend to have a high ionization energy and a high electron affinity. Metals tend to have a low electron affinity and ionization energy. As for the size, they're going to decrease going this way and increase going down. And so, the larger ones, once again, are going to be down over here. And so the non-metals would tend to have small radius, and the metals would tend to have a large radius. So, reading into that a little more. All right, I already did this. I already defined atomic radius. It measures the size. It's from the nucleus to the outer electrons. Ionization energy, the energy needed to remove. So energy needed to remove outer electrons, and this is the energy put forth to gain electrons. This one you make positive ions, this one you make negative ions, so cations, anions. Shielding effect. All right, so the shielding effect are the electrons that get in the way, is the easy way to say that. What they are is the inner electrons, not the outer electrons, that reduce the attraction the nucleus has for those outer electrons. So it reduces the attraction the nucleus has for the outer electron. So the fact that it reduces the attraction means, how is it going to affect the ionization energy? The ionization energy is a little bit lower. It's a little easier to remove the electron, so it requires less energy. So the ionization energy is a little lower. How does a half-filled P sublevel affect the ionization energy? Question mark. The way a half-filled P, remember we talked about levels of stability. The most stable you can be is an octet. Octet is greater than a filled S, P, or D. We don't really talk about the Fs. And that is a little bit greater than a half-filled sp, d, or f. And so a half-filled P will be somewhat stable. So this causes some stability. And the fact that it's somewhat stable means the ionization energy is going to be higher. So the fact that it's going to be a little harder to remove the electrons because of that stability, meaning it requires more energy. All right, metalloids. A metalloid is it has properties of a metal and a nonmetal. So it has properties of both. Maybe it shares electrons, but it's shiny, things such as that. Where are they located? The way we learn it, remember, is it's touching the stairs with two sides. So two sides of the element's box must be touching the stairs, starting with boron. And the exception is right there. Aluminum is a metal. So that's an exception. Remember, aluminum is a metal. But the others would be metalloids. How many outer electrons does nitrogen have? Nitrogen would have 5 outer electrons. The easy way to tell, well, the hard way to tell is its electron configuration is helium 2s2, 2p3. So it has 2 in the s and 3 in the p, 5 outer electrons. But I showed you on the periodic table the old method of naming the columns or the groups is with Roman numerals and the letter A. Column 1 is Roman numeral 1a, which would have 1 outer electron. Well, nitrogen is in Roman numeral 5a. So the Roman numeral will tell you, I completely wrote that wrong. Let's try that again. The people watching or reading just the worksheet won't see that. So don't tell them. So the Roman numeral and the letter A are the outermost electrons, the S's and the P's, and so 5A, or group 15, but subtract the D's. So 5. So 15, subtract the D's. Write the group names. First column are the alkali metals. Second column, alkali, or alkaline, usually as the second column, earth metals. Then we have the middle. These are the transition metals. Now we do call that the boron group, the carbon group, the nitrogen group. Oxygen groups, the one that starts with O is called a chalcogen. Didn't really mention that much though. Next one is the halogens. And then the last one are the noble gases. So noble gases. And that handles those. The two bottom ones are the lanthanide, which starts with lanthanum, and then actinide. Both of those are called the lanthanide and actinide series. So they're the Fs that go down the bottom. Multiple choice. Okay. Which groups contain all three, or which group contains all three states of matter? The only one that does are the halogens. The halogens start with F, which is a gas. Right below F is chlorine, which is a gas. And we're talking at room temperature. Then there's bromine, which is a liquid at room temperature. And then there's iodine, and there's acetine at the bottom, but we don't usually mention acetine much, radioactive sucker. And that is a solid. So both of those are a solid. All right, the octet rule. 8 electrons in the outer level. Remember, that means stable. Once again, the noble gases. All right, explain the circled exceptions to the trend in the following graph. This is an ionization energy graph. And ionization energy, you could see the pattern here. I'm talking about these two circles right here. So you can see we're going from lithium up to neon across the second period. So it goes lithium to beryllium, back down to boron, and then carbon, nitrogen, back down to oxygen, and then fluorine, and neon. And so why do we have those two exceptions? Well, it goes back to what I showed you with stability. The first exception there is beryllium. See, beryllium should be down here somewhere if you're going to follow the trend. Like right here would be where it normally would be. But it has a filled S sublevel. And again, there's that a little bit of stability, requires more energy to remove the electron. Then you go to boron, which only has 1 in the P. So it's not a filled, it's not a half filled. And so you go back to the trend, boron, carbon, nitrogen, and then back down again. So nitrogen really should be, somewhere in that area. But nitrogen has a half-filled P sublevel. So again, somewhat stable, requires a little more energy than we would think, and then it drops back down to the regular trend. You can see the same thing happens across the next period. Sodium going to magnesium, back down to aluminum, and then silicon, then phosphorus, sulfur, and then chlorine and argon. And so you can see the same trend. This, filled S, half-filled P. Once you get over here, the atoms start to get so large that the radius sort of affects those trends, and they're not as visible in the pattern. All right, so classify the following as a metal, non-metal, metalloid. So strontium being in the second column is a metal. Cadmium, transition metal. Chlorine is a non-metal above the stair step. Silicon. Silicon is touching the stairs with 2 sides. That makes it a metalloid. Antimony is touching the stairs with 2 sides, so that makes it a metalloid. And then argon, one of the noble gases, is definitely a non-metal. All right. I should have grabbed a periodic table and stuck it on here so I could show you, but I did not. So you can have one in front of you. I'll mention where they are in relationship to each other, though. All right, so we're trying to see which one has the larger radius. Remember, the trend is it increases in going in that direction, and it decreases going in that direction. So it increases down, and it decreases across. So we're trying to compare lead and silicon. So lead compared to silicon. Silicon is higher on the chart, or you could look at it as lead is lower, making it larger. Fe compared to CO. CO is to the right of Fe, making iron larger. Calcium or potassium. Potassium, because you go to the right to get to calcium. All right, now we have ions. Remember, to make a negative ion, you have to add electrons, and remember I showed you those pictures. It just about doubles the size. Again, the negatives would be larger. The positive, though, would be smaller because you are taking away electrons. Aluminum or chlorine. Aluminum because chlorine is to the right. Lead or bismuth. Lead because bismuth is to the right. Zinc and cadmium. Cadmium because it's lower on the same column. And then we have another positive compared to the atom. The atom is going to be larger because you take away electrons. It makes it smaller. Same number of protons pulling on less electrons, remember. Now, I didn't ask any where they're not in the same column or row. We didn't spend a whole lot of time on these trends. Normally, I would do that, and the increase going down would be greater than the decrease across, but I'm only going to ask them the easy ones. All right, ionization energy, and notice it's lower. And so we are looking for ionization energy which decreases, increases. So it decreases down, increases across, just like in the last one. I'm not going to ask any that are not in the same column or row. So we have lead and silicon again. So they're in the same column. We're looking for the lower one this time. And so you could say the larger radius. But that would be lower because it's lower on the periodic table. Iron or cobalt, it's going to be iron. Calcium or potassium, it's going to be potassium. Chlorine or fluorine, it's going to be, chlorine is lower on the same column. Sulfur or oxygen, sulfur is lower in the same column. Barium or calcium, barium's lower in the same column. You see a trend here. Aluminum or chlorine, they're in the same row, and aluminum is further to the left, so it increases until you get to chlorine. Lead and bismuth, and lead is further to the left, so bismuth will be a little bit bigger. And zinc or cadmium, you decrease going down, and cadmium is lower on the same column. All right, last one here. We are, remember I had another clue here which you were supposed to cross out. I was copy and pasting and I forgot to delete that thing. It had a 6 in it though, so this one was A through H, so that should have been a bit confusing. All right, so what this is the second period of the periodic table. So we have hydrogen here, we have helium here, and what we're trying to fill in are the 2 S's and the 6 P's of the second row, or the second period of the periodic table. All right, so I know what elements are there, so I can kind of look and cheat and figure out which one is a metalloid, and that would be boron. So A is going to go right there with the metalloid. There's only one metalloid in the second period of the periodic table. So I got A. That's definite. G has a larger radius than C. I don't know where they go yet, but remember the trend for radius is it decreases going in that direction. So G is going to go to the left of C, but we don't know where yet. D has the lowest electron affinity. Electron affinity has the same trend as ionization energy, increases going across, so the lowest is going to be the one all the way over there on the left. F is a halogen. Halogens are the second to last column. HB is a formula for an ionic compound. I'm going to come back to that one in a second. E is the dot diagram for E, so you can see it has its octet of dots, which makes E a noble gas. Okay, so now, HB is the formula for an ionic compound. I tried to make this one tricky because so far we've been looking at easier ones where you just cross the charges. There's actually 3 different opportunities for this to be HB if it's an ionic compound. It can be H with a +1 and B with a -1. It can be H with a +2 and B with a -2. Or it can be H with a +3 and B with a -3. Well, which one is it? Well, they can't be a +1 because D is in the +1 column there. So it has to be H as a +2 because the +3 column is taken. So if H is a +2, B is a -2, so that would go there. Remember, -2, -1, 0. So this is the right one. And so we got that. And then the last 2 then are G and C, so G is going to go there and C is going to go there because G has a larger radius than C. And they were the only 2 spots left. All right, so there it is, test review.